Describing motion is called kinematics. For this, we need to quantify time, position, velocity, and acceleration. Later on, we shall explain the motion largely by analysing forces, which are the causes of accelerations. Consider this motion, walking in a straight line at constant velocity. Measuring distance from the wall, the position is 3 metres, 4 metres, 5 metres, 6 metres. The velocity is constant, and distance from the wall is increasing by equal amounts for each second. So the slope of the graph of displacement x versus time t is constant. Note that x, the distance from the wall, is not 0 when time equals 0. We call that the initial displacement x0, and so we write x minus x0 equals vt. Or alternatively, x equals x0 plus vt. The velocity is the rate at which the displacement changes in time, so we can calculate it by taking the derivative, dx dt equals v. Or we can obtain the displacement by integrating the velocity. X is the integral v dt, which is vt plus a constant of integration. Now, at t equals 0, x equals x0, so the constant of integration here is x0. In other words, x equals x0 plus vt. Either run through that much again, or else let's add acceleration to the motion. We just saw that velocity is the rate of change of displacement. Acceleration is defined as the rate of change of velocity. If acceleration is constant, then velocity is changing at a constant rate. Now the velocity is 0, 1 metre per second, 2 metre per second. The acceleration here is positive, which means the velocity is increasing, which means that the displacement time graph is getting steeper. Once again, note that, for this particular example, the x0, the position when the clock starts, is 3 metres. Let's calculate the velocity in the x direction by integration of the acceleration in that direction. For constant acceleration, integrating a with respect to t gives at plus a constant. Again, use a subscript 0 for initial velocity, so the constant of integration here is v0. To get the displacement x, we integrate again, and now there are two terms to integrate. The first term is constant, so integrating it, as before, gives a linear term in t. Integrating the second term, however, gives a quadratic equation. As before, the initial condition gives us the constant of integration, so the x displacement as a function of time is x equals x0 plus v0t plus a half at squared. That's the equation of the parabola we can now see. Check that when you take the derivative of this equation, you get our original equation 1 back again. Now let's look at the case of negative acceleration. In this example, we start with a positive velocity, i.e. going in the positive x direction, but we slow to a stop, then acquire successively more negative, i.e. backwards, velocity. Let's collect these useful equations. Integration of the acceleration gives us equation 1. A second integration gives us equation 2. If we use equation 1 to eliminate t from equation 2, we get another useful equation, one that relates the distance travelled to the initial and final velocities. Do you need to remember all the equations we've seen? Well, those for constant velocity come from this set just by setting acceleration equals 0. And you can quickly derive these three equations. However, you can't really say you've understood a topic in physics until you've done quite a few examples using it. Once you've done that, you probably will know these equations by heart.